our last video, we learned about binomial distributions. In this video, we're going to focus on two special binomial distributions, a geometric probability distribution and a negative binomial distribution. If you recall in the last video, in the binomial, it had an outcome, either yes or no, or for or against. There are two possible outcomes, but we could find, let's say, 6 out of 10 people voted this way instead of this way, and the order of those people didn't necessarily matter. We found all the different combinations that was possible. But in this case, this first special case in the geometric probability distribution, we're looking for a specific, in this case actually the first success, to be on any number of trial that I run. So I can say, what's the probability of my first success being on the third attempt? So we can also use the same formula we used last time with a little twist. We don't need the different combinations because we know exactly what location we want the spot to be. The expected value in this case, the mean here is going to be 1 over the probability of success, and the standard deviation and variance are the probability of success divided by the probability of failure squared, and then the square root of that. Okay, so let's get into it so you can see when to use which probability distribution. Here we have a bullseye. So there is a 15% chance of hitting a bullseye on a dartboard. So we're counting this as binomial because you either hit it or you don't hit it. So there's a 15% chance that you do hit it. So that means P is 0.15. And then if we take that number and subtract it from 1, excuse me, we get the probability that you're going to miss the bullseye, and that gives us 0.85, or 85% chance that you miss. Okay, so we can fill out a table here by multiplying this probability together. Because they are independent, so we'll have to use the multiplication property. Now, if you throw a dart and you hit it on your first try, well, then there is a 15% chance of hitting it on your first try. So that would be the probability of 1. And then if you hit it on the second try, the probability of 2 would be, well, we missed it on the first try, right? So there's the probability for missing it. And then on the second try, we made it. So then we multiply it times the probability of hitting that bullseye. And that would give us the probability of getting a bullseye on the second turn. And then that's how you fill this out. Every time you miss, you multiply times 0.85. And then when you hit the bullseye, then that is the 15%. So the formula, if you look at it, is the number of shots that you take minus the one that you make times the one that you make. So we can keep doing this table by using that pattern. So P of 3 means I'm going to have 2 misses. I missed the first one. I missed the second one. So that gives me 0.85 squared, 2 misses, times the 15% that I hit it on that third try. That leaves me with 0.108. And then on the fourth try, the same thing. I just need to change the exponent to 3 because 4 minus the one that we hit is going to be 3. So if you look, we're building the formula right now. And that one is P of 4, and P of 4 in this case is 0.092. I'm just inputting these numbers into my calculator. And then for the 11th try, so now I can ask you for any tryth number because we know the formula, we know how to use it. So we're going to jump all the way to the 11th, and you'll see that it's just the same. Instead of 11 in the power, we're going to have 10 misses and 1 hit. So when I multiply those together, that gives me a 0.03 chance, or a 3% probability that I miss 10 shots and hit my 11th shot. The expected value for this situation, the mean, is 1 over the probability of success, which is 1 divided by 0.15, and that's about 6 2/3, or 6.6 repeated. So this, I could expect to throw 6 or 7 shots before I hit my first bullseye. So 5 or 6 shots, and then I'm going to hit a bullseye. The variance is going to be sigma squared is the probability of success over the probability of failure. Probability of failure divided by the probability of success squared. I think I said that backwards earlier. So 0.85, our failure, divided by the success squared will give us our expected variance in the number of attempts we need to make till we hit our first bullseye. So about 37.7 until I get my first bullseye. And then if I wanted my standard deviation, I just find the square root, 37.7, and that is approximately 6.14. Okay, I'm going to do another one. This time I'm not going to make the table. We're just going to work this out as they ask us. Okay, there's a 35% chance of making a basket on a free throw. Throws are independent of one another. Good, that's important that they're independent. We can say either you make it or you miss it, which makes it a binomial distribution. We know that our probability of success is 0.35, and my probability of missing it is 0.65, because that is 1 minus 0.35. Okay, so now I can find the chance that the first basket occurs on the third try. So if you're a visual person, we threw a shot and we missed it. We threw a shot and we missed it. We threw a shot and we want to make it. So what is the chance that this happens? Well, that would be the probability of 3. That's my y value or my x value. So using the same formula as before, we take the chance of failure, and however many there were 2 failures, and then the chance of success, and there's only going to be 1 in this type of situation. I don't know if I mentioned that before, but this one we're looking for just the first success. We're not looking for all possible successes. We're just looking for the first time that you're going to make it. So we only ever have 1 of these in a geometric probability, 1 success. When I multiply those together, you get the probability of 3 is 0.148. Okay, now the chance that the first basket occurs at most on the third try. So this is a PDF, right? Probability distribution function. Anytime you have at most or at least, you have a cumulative function. So we're going to have to find all of the probabilities of each outcome and add them up. So the probability that we have at most on our third try. So let's see, the probability of making on the first try means that I have 0 misses and 1 make here. Then I need to add that up to the probability of not hitting on the first try, but instead hitting on the second try. Oops. So there's 1 miss and 1 make here. And then we need the probability of the third try. So I missed it twice, and then I made it on the third try. So I did the same thing that I did in this problem, but because it was cumulative, I had to do it for 0, or for making it on the first try, making it on the second try, and making it on the third try. When I add all those probabilities up, I get 0.725. So there's a 72.5% that the first basket will occur at most on the third try. What's the chance that the first basket occurs at least on the third try? So, because we already have this information, actually we don't. Okay, so what we could do is say that this is the same as 1 minus the probability that you make it on, at most, the second try. Because if we can find this probability and this probability, then I can say, now the rest is really what we're looking for. Does that make any sense? We're going to subtract the whole outcome from these two probabilities together. So the probability of making it on the first try plus the probability of making it on the second try. So 1 miss, 1 goes in. And then if I plug that in my calculator, I get 0.423. So there's a 42.3% chance that the first basket occurs at least on the third try. So the expected number of attempts that I can throw until I get the first basket is 1 over p, which is 1 over 0.35, and that is 2.857, so about 3 until I get there. We kind of saw that as a sweet spot here. And then variance, oops, my sigma's going crazy, is failure over success squared. Going to show us our error here. Okay. Do I have more? Now, you don't have to do this by hand. There's usually a code for this. But it's super easy, so you really can just multiply the number of misses times 1 success, and you get what you're looking for. So what is the probability of getting the first 6 on the 4th roll of a 6-sided fair cube? This is most likely how you're going to see the problem. It sounds ridiculous, right? So just break it down. We're looking for probability of getting the first 6. So that's our outcome, the first 6 on the 4th roll. So that means we have 4 spots. We want the first one to happen here. So these are all misses. So usually drawing yourself a little picture like this will help you tell which distribution you're using. This tells me, because I have to get the first one here, that this needs to be geometric, because geometric focuses on the first one and order is very specific. So miss, 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 make. So I don't need any combinations because I know the exact combination I'm using. So if I just take the number, the probability of success and failure, so I need my Q here, and there are 3 failures, and my success goes here, and there's going to be 1 of them. So now I'm going to go back to the problem, and I'm going to figure out the probability of getting a 6. So it's a 6-sided fair cube. So the probability of just rolling a 6 is 1 over 6. So that would be our probability of success. The probability of not rolling a 6 would be 1 minus